Dear students, parents, teachers, and friends of Colegio Catamarã, good afternoon. I'm Joanna Freeland, the English coordinator at Colegio Catamarã. I would like to introduce to you Sergio Bleckmann, our head of the senior school.
Hello, Joe.
We thank you all for participating in this live organized by our school, which has 25 years of tradition in education and human development. And we especially thank Dr. Paul Brugarolas, who we are honored to present to you and who will talk to us about the Mars 2020 mission and the launch of the rover Perseverance to Mars, which, among other objectives, intends to search for traces of past microbiological life on Mars, as well as to collect data on the Martian environment that can guide possible future manned missions to Mars. This rover also intends to be the first part of a project that aims to bring samples of Martian soil to Earth for the first time. At this moment, I ask Dr. Brugarolas for permission for us to give his CV to you in Portuguese. Sergio Bleckmann, please.
Thank you, Joe. Paul Brugarolas é engenheiro formado pela Universidade de Navarra, em San Sebastián, na Espanha, e recebeu o título de PhD pela Universidade do Sul da Califórnia, em Los Angeles. O Dr. Brugarolas ingressou no laboratório de propulsão a jato da NASA em 97. Ele trabalhou nas seguintes missões: a MLS Curiosity, precursora da Mars 2020 Perseverance, a Spitzer Space Telescope, a Cassini e o Shuttle Radar Topography Mission. O Dr. Brugarolas é atualmente o engenheiro-chefe de navegação, guiamento e controle da missão Mars 2020 Perseverance. Bom, eu preciso explicar também para a comunidade do colégio como será a mecânica dessa live. O Dr. Brugarolas terá 40 minutos para sua exposição e depois nós teremos cerca de 20 minutos para as perguntas. É importante que as perguntas sejam enviadas via YouTube e a nossa equipe selecionará as perguntas que serão feitas ao Dr. Brugarolas. Joe, acho que agora você pode deixar o doutor à vontade para começar.
Please, Dr. Paul Brugarolas, we pass the word over to you.
Thank you for the introduction. So let me get it started here. Let me share my screen.
While you are starting your screen, I would like to tell our audience that every week we have a live presentation that Colegio Catamarã is offering on all of these fascinating subjects. Thank you.
So good afternoon, everybody. So today I'm going to talk to you about the Mars 2020 Perseverance mission. As you can see here, it's a rover we're going to send to Mars. The launch window is going to open tomorrow. Tomorrow at 4:30 a.m. Pacific time in California. And basically, we're going to take a journey to Mars. So I'm going to tell you a little bit more about the mission first, and then I'm going to focus the main content of today's talk on landing on Mars. We're going to be landing on Mars in February 2021. So let me get started here. You can see here this diagram that shows past missions to Mars and future missions. You can see here in the recent years, we basically have the Mars exploration rovers, which were Spirit and Opportunity in 2003. Then we have in 2007, the Phoenix lander. In 2011, we landed the Curiosity rover. In 2018, we landed another lander in the North Pole called InSight that had a seismograph that measured Martian earthquakes. In 2020, this is our mission to, in 2020, there is a European mission called ExoMars. Unfortunately, this got delayed to 2022, so we'll not be able to see that. And then in 2020, we have the Mars 2020 Perseverance rover. In order to do these missions on the surface of Mars, we also need support from satellites. You can see here the current fleet of satellites that NASA has and the European Space Agency has at Mars. We have Mars Odyssey, Mars Express, Mars Reconnaissance Orbit, MAVEN, and the ExoMars Orbiter. This is very important because this is how we get our communication link with our surface spacecraft. And the other thing that is very important, we use cameras on these and instruments from these satellites to study Mars, and this is how we pick where to land. It's basically based on the scientific discoveries from the satellites. It will tell us what is exciting places to go. You can see here on the right, you can see a picture of Mars today. On the left, what you see is what people think the past of Mars was. We know that many thousands of years ago, Mars had water, and it was like Earth. And this is one of the things that brings a lot of interest to the scientists. They want to understand what happened to Mars. Part of it is to learn for our own planet. We don't want our planet Earth to end up turning back like Mars, a very dry place with no water that hardly can sustain life. So this is a lot of the motivation of going to Mars, is to learn about Mars, learn about potential, why did it change, and what can those things happen to Earth. And at the same time, given that at some point Mars had water, the scientists are very interested to finding if at some point in the past, if there was life in Mars. So in order to answer these questions, we basically built a spacecraft. In this case, we're sending a new rover, which is this Perseverance rover. You can see here this rover. Just to give you an idea, the height of the rover is roughly 2 meters tall. And the size of the size of this rover is roughly the size of a small car. And it weighs roughly 1,100 kilograms, 1,100 kilograms. And the question that we're going to answer in this mission is, did Mars ever have life? So in order to answer this mission, the scientists have created 4 main objectives for this mission. One is to study the geology, one, the astrobiology, sample caching to bring back to Earth so we can further study materials from Mars and do a very detailed analysis in laboratories in Earth. And also prepare for humans. We have experiments on board the rover. In particular, we have an instrument that allows to convert carbon dioxide from the Mars atmosphere into oxygen. So it will be an experience that will allow us to test technologies that are needed when we will have for humans in the surface of Mars. So to achieve these goals, for the first goal for geology, the science team wants to look at the geology at different scales. They want to understand the context at the kilometer scale to understand what kind of topographic features there are and basically geologic formations. Then they want to go down to a lot of smaller formations at the 1 meter, looking at the context of the rocks, if they're stratified or not. Then they want to go down to the centimeter level. This is basically with a set of camera suites that the rover has. And then to the millimeter level with basically zoom lenses in cameras, but also spectrometers that will allow you to evaluate the chemical composition of the materials. And not just in the surface, the rover has a robot arm that includes a set of tools like a drill and a scoop that will allow us to basically find and analyze subsurface materials. So that's the first goal. The second goal is to look at the astrobiology. And the idea here is to look at areas that potentially could have harbored life in the past. And the main objective here is going to areas that we believe there were areas that in the past of Mars were wet, basically bottom of lakes or rivers, such that you can then find what you see on the equivalent places in Earth, like clays and things that actually contain signatures of life in Earth. So the idea is go to Mars, study those places, and basically analyze the samples and see if we see similar compounds that we can give us hints of life in Mars in the past. The third objective, as I said, is to collect samples to bring back. Even though the rover has a very complicated set of instruments, the instruments that we have on laboratories on Earth are even more sophisticated. So like we did for when the Apollo missions to the moon, we brought samples back from the moon that there's still been research done on them. This is the objective also for this part of the mission, is to bring samples back so we can do very detailed analysis on Earth of those samples and learn even more. And those are things that we cannot do with the limitations of the instruments that we have at Mars. And as I said, the fourth objective was to basically prepare for humans. And that's the instrument I was telling you that is going to demonstrate generation of oxygen at Mars. So these are the objectives of the mission. And now what I'm going to do is I'm going to briefly talk to you about how to get there, and then we'll focus talking about the landing. First thing to mention is that our landing site, basically, as I said before, there was the science community was asked to find what the best landing site was, and what they did is looking at imagery and instruments from the Mars Reconnaissance Orbiter, which is one of the NASA satellites. They identify a crater called the Jezero crater, and it's a very interesting crater because it has a delta of a river that comes into it. And I'm going to show you some images later, but it's a very exciting place because we actually believe that there was flowing water there. And where we're going to go, the science team is very excited because they believe they will find very good samples to bring back. So I will step through these steps of the mission briefly. So let's just go next. So when we're going to Mars, you can see here actually the spacecraft as it's finished in one of the space simulators at the Jet Propulsion Laboratory. This is the deepest space simulator. The deepest space simulator, you can see here, it has very thick doors. We can take this whole room in here and pump it down to pressures equivalent to the vacuum of space. In addition, this simulator has a set of incandescent lamps that it could create the equivalent of the heat of the sun. And in addition, it has a refrigeration system that you can take it to the very low temperatures of deep space by use of nitrogen and liquid nitrogen. So what we do is, as we build these missions, before we send them out there, we're going to basically test them in chambers like this to make sure that they will work as expected when we get to space. So all this is done. We're now at the step that we're basically waiting for launch. As I said, launch could happen as early as tomorrow morning. And then we're going to start, basically, we're going to separate from the launch vehicle and we're going to get on our way to Mars. And you can see here, this is our vehicle as it flying to Mars. You can see here this is the entry capsule. And back here is what we call the cruise stage. This is a spacecraft, a small spacecraft that is going to take us from Earth to Mars. And right before we go into the Mars atmosphere, we're going to separate from it. What you can see here, this spacecraft has solar panels on one side. It has, you can see here a little bit, this is a camera that looks at the stars. This is going to be our eyes as we're flying to Mars. We have a camera that as you look at the stars, we have a software application on board that detects which star those, and comparing to a map, it will tell us which way are we looking, which way the spacecraft is pointed. And the other thing you can see here is this a little bit thruster pod. So when we need to make corrections in our way to Mars, we're going to use these little thrusters to fire little puffs and basically control the spacecraft in its way to Mars. It will take roughly 8 months. Basically, we're launching, as I mentioned earlier, the launch window starts tomorrow. We have a window that will last 15 days. And we'll get to Mars February of 2021. When we get to Mars, as I said, we're separated from the cruise stage. And basically, as we enter the atmosphere, Mars has an atmosphere that is 100 times thinner than Earth. But still, because we're coming in at very high speed, you create a lot of heat. That's why we need a heat shield to protect for it. So what I'm going to show you later is an animation of of a simulation of how we go to Mars. But what I'm going to do now is kind of give you a little bit of a more detailed description about what happens here. So when you see the movie, you have some context. So as we enter the atmosphere, the vehicle, it has these thrusters, and it's going to be doing a guided entry. Basically, it's going to be aiming for the right place, for the Jezero crater. And it's going to be flying with a very similar algorithm that the one that was used by the Apollo missions in the 70s when they were returning from Mars to Earth. So we enter Mars, and basically we have, we're going to, as we separate from the cruise stage, basically it's going to take us roughly 10 minutes to get to when we start sensing the atmosphere. When we sense the atmosphere, we're going to basically fly through the atmosphere for roughly 2 or 2.5 minutes, aiming for the right point. And then at that point, basically, we're going to open a parachute. We're going to open a parachute, which is a supersonic parachute. Just to give you a feel, the diameter of this parachute is 21 meters in diameter. It's very big because the Mars air is very thin, so you need a very large diameter. And we're opening it at the equivalent of a Mach 2. That's twice the speed of sound at Mars, which is roughly 450 meters per second. Once we're on the parachute, basically we're going to then eject the heat shield, and we have a little camera in here at the bottom of the rover, which is going to basically do. Actually, here's a better picture. This is the bottom of the rover. You can see how the wheels of the rover are collapse upwards, yes, so it can fit on the back shell. And around approximately over here is what this camera that I was telling you about is. And this camera, what it's going to do is basically, actually, I'm gonna talk about the camera a little later. So let's just say we descend on the parachute. Once we get to the right altitude, that is roughly 3,000 meters over the ground, is when we're going to separate from the parachute and start what we call the power phase. Basically, we're going to use our landing engine, which are very powerful rockets, to land the vehicle. In order to do that, we use these rockets, but we also need to sense the ground. So what you can see here is, you can see this plate over here on the side, and this plate has radar antennas on it, and these antennas is going to measure where the ground is. It's going to measure our altitude to the ground, but it's also going to measure our relative speed to the ground. In addition to that, we also have over here an inertial measurement unit, which is like a device that like you have it inside your cell phone that measures, like when you play a game, that it measures how much you move. It's exactly the same. So basically, that unit, it's a navigation grade unit, allows us to measure the relative motion with respect to a reference frame. And with the combination of the radar and that IMU is how we land on the ground. So at the end, basically right before, roughly at about 21 meters from the ground, is when we're going to get ready to basically touch down. For that, what we're going to do is basically we're going to do what's called the sky crane maneuver. Basically, we're going to release the rover in 3 bridles, and basically release the rover, then release the wheels, and start coming down at the slowest speed until we touch down. When the spacecraft detects that you have offloaded the weight of the rover, we will cut the bridles, and the sky crane, the descent stage, which is performing the sky crane, will fly away and crash at about 600 meters away, and it will let the rover on the ground on its wheels, ready to start his science mission. This is what I was telling you before about the camera in the rover. It's going to do, this is a new technology we done for the Mars 2020 mission, which is basically at the end of the parachute, the camera is going to take pictures of the ground. It's going to compare them with a map that we have on board, and from comparing the images with the map, it's going to figure out where we are. And based on that map, then we're going to figure out where we want to land, a safe target where to land. Because as we're coming down in that delta, you don't want to come down on the side of the hill of the delta. You want to come down on a safe spot. So this is a new technology that we have designed for this mission, and we're going to be basically testing it for the first time in a NASA mission. And once we touch down, basically, we're going to basically start to explore Mars. So what I'm going to do now is tell you about the landing part in more detail, and also highlight some of the technologies that we have, and that will be the main focus for the second half. So I'm going to switch to a different presentation really quickly. I want to show you something here. So can you see my screen now? Can somebody confirm that? Can you see that it says every Mars landing attempt ever?
No, Paul. You need the screen to open your screen share.
Okay, let me switch to the screen sharing 1 second. Okay, hold on. Screen share. There we go. All right. Do you see it now?
Yeah, that's fine now.
Okay. So this is a poster put together by the Planetary Society, and it shows here. This is a map of Mars. It shows the different landings on Mars, and you can see here on orange the successes. It shows you the failures, and it shows future missions. When you can see here is that we have basically attempted landing on Mars quite a few times, but there has been quite a few failures, as you can see here on the ones that are on gray, because it's difficult. Landing on Mars, you're going to a different planet, a different atmosphere that we don't know much, different gravity. It's roughly a third of Earth, and there's a lot of unknowns, and everything has to be autonomous. One thing that I want to mention here is that this year, 2020, the Perseverance rover is going to go here to the Jezero crater. But there is also a Chinese mission that is going to Mars, and it's going to land a rover. The Chinese mission is called the Tianwen one. It was launched a week ago. It's on its way to Mars right now. They haven't chosen the landing site. They have 2 candidate landing sites. You can see here in blue. And that mission is also going to get to Mars around the same time frame that we are, in about February of next year. But that mission has a satellite and also a lander. The satellite is going to stay in orbit for about 3 months, and then it's going to deploy the lander, which will land a small rover, smaller than the Perseverance rover, in Mars in the spring of next year. And it's also very exciting to see what they do. So now let me tell you a little bit more about landing Perseverance. And I'm going to go and actually share to a third package that I'm going to show you some of the landing technologies. Okay. So now. Okay. So what I'm showing you here, it's what you can see here is the Jezero landing site. This is our landing site, the one that says Mars 2020. This larger crater here, this is actually the Jezero crater. It's actually very large. To give you a sense, this is the size of our landing ellipse. You can see the size is roughly 7 by 7 kilometers by 6 by 6. And in order to achieve the size of landing ellipse, we actually had to develop a new technology. What you see here is the size of the MSL landing ellipse. This was the Curiosity landing ellipse. The way that Curiosity achieved this landing ellipse is doing entry guidance, like I told you before. But for us, in order to squeeze it farther down to this, we basically change what we call the parachute deployment trigger. This is the trigger that basically decides when to open the parachute. And by coming out with a new algorithm for 2020, we can, as you can see, we can reduce the ellipse substantially to a lot smaller size. The other thing that I want to point out here, you can see here that if you don't have entry guidance, your landing ellipse are a lot bigger. This is important because when you have to certify a landing site for safety, you need to look at the landing hazards for the full footprint of the landing ellipse. So having a small ellipse is quite beneficial from the amount of work that you need to do, and also finding an exciting place to go that you can put that landing ellipse right where you want to go. So this is one of the key technologies we have developed for landing on Mars. The next thing that we had to do for Mars 2020 was actually, and I'm going to pause this movie, is is we had to qualify a new parachute because we have a heavier rover. And that means that when you open the parachute, you're going to have a bigger loads. So we had a program here at JPL to design and qualify new parachutes. And part of designing and qualifying a new parachute is you try to test it in a relevant environment. In this case, we went to NASA Wallops. It's basically one NASA center on the East Coast that they test sounding rockets. And we did a high atmosphere test because on Earth, the high parts of the atmosphere have similar densities and when you encounter on Mars. So we basically put our parachute in a sounding rocket and tested there. And we're going to show you. I'm going to show you a video of that qualification. So you can see here the sounding rocket going up. You see basically separating from the sounding rocket separating from the lower stage. What you can see here is that the upper stage is spinning, so that's why you see the light going around like that. And what you're going to see now is that these are the cameras on board. Basically, ejects the nose cone. Now the parachute payload is exposed, and now we're going to wait for the deployment of it. You can see the Earth horizon at the bottom. And now you're going to see the deployment of the parachute. So, so this is our parachute. You can see it got fully inflated. And basically what we're looking for and when we do these tests is that we put cameras like this for context, but then we also put cameras like this, which is a really high speed cameras. It's like 1,000 frames per second that allow us to basically see how it separates and how it inflates at very high speed. So we can actually understand the dynamics of the inflation and also understand if there is the performance of the parachute during these events, which is key for understanding the performance of the parachute. You can see here as the parachute, it's opening slowly, and it's inflating slowly. It is you can see motions that are similar you will see on a jellyfish, and you see as the parachute inflates, and this allows us to analyze the performance, and this is and make sure that that the inflation is as expected, but also allows us to see if there was any damage. And then after the flight, we will recover the parachute from the water and make sure that there is no rips and damage to it. So this is the second key technology that we have added for Mars 2020 for landing at Mars. The third thing is I showed you it was this terrain relative navigation. So we developed this new technology. We had to develop a new sensor. And in order to make sure that it works, we basically, what we do, okay, this is a zoom version of the Jet crater that I'm showing here, but we had to basically, I'm gonna show you here, we built that technology and then we basically put it on a helicopter in Earth and went and tested in the deserts in California to basically make sure that terrain relative navigation technology works. What you can see here is in the front of the helicopter, we have placed so sorry for the noise, I didn't realize it was so loud, but you can see here on the front of the helicopter, basically, we have mounted that new sensor that we have developed, and we have taken it for flights on the desert to demonstrate the technology. I'm gonna show you, sorry, next page. This is a view from the helicopter of showing that sensor. It has the camera on one side, it has the gimbal in the other, and this has an IMU, so it combines information from both. And basically what you can see here is, as we're flying through the California deserts, is taking measurements. This is what you see from the helicopter point of view. If you now look at from the point of view of the sensor, what you're going to see here is, just to give you context, the movie has 3 parts. The part on the left is the map that we're going to match. The part on the right is actually the camera from the sensor, the image from the camera. The part of the bottom on the right is for context. So what you're going to see here is that as you take an image before it starts, this is the red box. What the software is going to do to find out its localization is going to do 2 steps. An initial step is going to put 5 boxes and match terrain on those 5 boxes on the ground from the image to the map, and then that computes a solution that is accurate to 200 meters. Once it gets a solution that is accurate, it does a second step that instead of doing 5 templates, it's going to do like 100 templates that will allow it to compute a solution that is roughly 30 meters in accuracy. So let's play the movie, and you're going to see that as the movie goes, this is basically, you see, it takes these coarse images, it found the solution, then it takes the fine images. What you can see here is that the green boxes are the ones that match those templates. The red and yellow boxes were false matches, which they get thrown out. And based on the green solutions, we will come out with a map relative localization that is used for deciding where to land. So this is the 3rd key technology we have designed for landing on Mars for the Mars 2020 mission. So I'm going to skip through this. There are different movies and different. Okay, so actually let me restart this one. So those were movies from the testing on the ground. This, what I'm going to show you now, is a simulation on Mars. You can see here is a model, the map from the Jezero crater. And we're going to basically run the same software you saw through a simulation, exercising the full same software is to make sure that and test it to see how well it works. And you can see here, this is our prediction of how things will work at Mars. And what you can see here in this movie is for a given flight trajectory, how basically follows the same steps, is able to track features and come up with a solution as we're coming down through Mars. And what you can see here is as the template moves to the left, that's basically the simulated motion of the capsule hanging from the parachute that tends to do coning motions. So now, to finish my talk, what I want to do is basically show you an animation of landing on Mars. This is basically is going to show you, this is from a realistic simulation. When you're going to see thruster firing, you're going to see the vehicle flying. This is a real trajectory flying to Mars based on a simulation. Just to orient yourselves, here you can actually see altitude, you can see speed, you can see acceleration, you can see Mach number, basically in terms of the speed of sound on Mars. You can see our fuel mass. When we start, basically we carry 400 kilos of fuel to be able to land the vehicle. And you can see here the fuel remaining. So I'm going to play this now. And so this is the simulation starts after cruise stage separation. We are basically spinning. The first thing we do is de-spin the vehicle. And now we're basically going to wait, as I was telling you before, until we sense the atmosphere. So right now what we're doing is basically you see little thruster firing, just holding our orientation such that we enter with the heat shield forward when we hit the Martian atmosphere. So we're waiting basically. The simulation is faster than real time. In real time, this is roughly will take roughly about 10 minutes after cruise stage separation. I'm just going to wait till we get there. So now we're going to start. We now enter the Mars atmosphere, and basically we're doing this entry guidance that I'm telling you. You saw the vehicle rolling to the left. So what the vehicle is going to do, it has a CG offset, which gives it a lead vector, And by modulating the vector allows you to control the downrange. And when it gets two sideways cross range, it basically turns them around and it goes the other way. So it's going to be doing these zigzags, getting into aiming for the Jezero crater. And it's going to do 3 of these reversals. They're called bank reversals. And once it completes the third one, we're pretty much lined up. It's going to go to an orientation called a lift up. Basically, it's going to be waiting then for the right time to that parachute trigger that I was telling you that allows to have a very small ellipse. You can see here a map of the terrain on the bottom, but also the terrain, you can see the different colors. The different colors, the blues and the greens tell you those are the safe spots to land. The red are the unsafe spots to run. It has basically the walls of the delta. You can see here that now we have opened the parachute. You can actually see the dynamics of the parachute, how the capsule is rocking below it. We're gonna roughly around now is when we're gonna eject the heat shield. We basically ejected the heat shield. You can see the heat shield being ejected. Now we're gonna wait for the radar. You can see here, these are the radar beams as they start intersecting the ground. Basically, we have 6 radar beams. As they intersect the ground, it's gonna allow us to solve for the altitude with respect to the ground and the velocity with respect to the ground. And and at this point is when we are waiting to get to 4,200 meters over the ground. At 4,200 meters over the ground is when we're going to turn on this terrain relative navigation sensor. That sensor is going to start taking pictures, as I showed you before. And then when we get to 3,000 meters over the ground, basically is when we're going to separate from the back shell and basically make a decision of where to land based on the localization information that we got, and separate and fly to that point. So what you can see here is that pink area on the ground is the field of view of that TRN camera. Right now is what I was telling you, we separated. Those 2 wedges on the right, our reachable space, we're gonna pick a target in one of those 2 wedges to land. We're gonna pick the safest target of all in those 2 wedges. As you can see, we picked the wedge on the left, and now you can see the vehicle flying to the landing target is doing a sideways divert. Just to give you a sense, this outer ring over here is 700 meters away from the center of that of the divert of where we started. And basically, we now start the vertical phase. Basically, we'll start going down, decelerate, and now you can see the parachute landing back there. And now we deploy the rover. And start going down slowly at less than 1 meter per second until we touch down. We have a piece of software that estimates how much weight of the rover you're carrying. And when we detect that we have offloaded the rover, we'll basically separate, and basically we fly away the descent stage and toss it away farther away so it doesn't fall on top of the rover. So this is how we're going to land in Mars in February next year, and you can see here the simulation finishes showing that the MRO orbiter and the Mayberry orbiter are passing above us. We basically have changed the trajectory so we can get communication right after landing and get the data from landing. So I think with this, this is the end of my presentation. I would like now to take any questions that you have.
Yes, Dr. Paul Brugarolas, we have many questions. Is that okay, Sergio? Would you like to ask a question?
Não, Joe, pode continuar. A nossa equipe recebeu muitas perguntas da comunidade e agora a Joe vai dirigir ao Dr. Brugarolas as perguntas que a gente recebeu.
The very first question is, what were the biggest challenges in carrying out this project?
The biggest challenge is, so it depends on the areas. One big challenge is actually the scientific instruments for the rover that are all new. So when you develop new instruments, you design it from scratch, especially the sample caching system is very complicated with the test tubes and everything. So that was a big challenge to develop that new instrument. From the point of view of landing, the biggest challenge was developing that terrain relative navigation sensor. It's a new technology, and as we develop it for the first time, you need to make sure it's going to work right. And part of it is you built initially a concept, then you built a prototype of the hardware. You take it to the desert, you test it, you go back to redesign it, then you finance the design, you qualify the design for your design criteria, but then we take it back to the desert. I was showing you with that helicopter to test it again, make sure that everything works. So that's been a long journey that we started since 2012. So we've been working on that sensor for 8 years, and now it's coming out to fruition. We're gonna see it operating in Mars in February of next year. So the challenges are the new things, and even though they're challenging, it's also fun. You get to do you get to do a new thing, and you get to design it from the scratch, and it's a lot of fun as an engineer to start with a white piece of paper and define what you want to do and take it through the design cycle. It takes a few years, but it's also very rewarding.
Exactly. A huge sense of achievement after so long to create these.
Yes, and although we're going to wait until February and make sure everything works before we can test.
I have a wonderful question now. Everyone watching is very keen. So they would like to know what recommendations would you give to teenagers that would like to work for NASA one day?
So my recommendations is that there are many ways to work for NASA. You could be as a scientist or as an engineer, so you have to pick your path. Many different kinds of scientists, like scientists or geologists, or same thing for engineers. Could be a mechanical engineer, electrical engineer, or and you have to think about what you want to do, what part of the work you like, and then as in high school, you probably might not know too well what you want to do. When I was in high school, I knew I wanted to do engineering, but I actually did not know that at the end, what I wanted to do is what I am today, which is I'm an autopilot engineer. I study electrical engineering, and then I specialize in control systems. So what I would recommend is take one step at a time, see what you like, make one decision at a time, and as you go, try to get as much practical experience as you can. And what I mean practical experience is right now, there is a lot of opportunities in the school for like engineering clubs or programming classes. Get engaged on those, so you get a sense of working on real projects, and that will help you line up your next set of decisions when you get to university where you want to study. You get to learn more about what things you like more to do and other things, and take one step at a time and keep on going. My path on getting into NASA, I mean, as Sergio said in my introductions, I studied in Spain electrical engineering, and then I went to the United States, to Los Angeles, to do a PhD in control systems. And halfway through, I got really excited with NASA, and I got a summer job at the Jet Propulsion Laboratory. And at the end of that summer, it was actually, that was in 1997. That's when the Mars Pathfinder mission landed on Mars. Some of you might remember, it was really exciting. It was a time that JPL had a lot of work actually at the end of that summer. They offered me a job, and I ended up, since then, I've been working there. But it is, my recommendation is take one step at a time, see what you like, and keep on follow your dreams. There are opportunities out there, and you have to keep on chasing them.
Thank you. That was very interesting, very inspiring for our youngsters. Also, Dr. Brugarolas, Sergio Bleckmann has a question for you, which is, what has been the most significant technological development that has made bringing samples from Mars possible? What would you say was the technological development that is making this possible?
So, so in order to bring what this mission, the 2020 mission, is going to do is collect them. And now working on the design of the next missions to bring it back. The technologically, bringing samples back is doable. We have brought samples back from interstellar dust, and so technologically, the technology is there. What it requires, what has been the key for this mission, is you need the commitment from NASA on the to basically to achieve bringing samples back from Mars. It's very complicated. You need the first mission to collect them, then you need a second mission to land basically a rocket on Mars that can launch it into space, put it on orbit around Mars for a future mission to grab it and bring it back. So basically, bringing samples back, like 3 or 4 missions together, and that's a very high cost for NASA to develop that. So for NASA to commit to something like this, it's a big commitment on the funding, and it means it's a program that is going to last like 20 years to complete, and we started in 2012. So the next, we're going to collect the samples over the next 2-3 years on Mars, and then they're going to be coming back. So it's probably going to take another 10 years to come back. So technologically, I think that we have improved things. That, for example, the terrain relative sensor that we have done allow us to go to exciting places to collect samples, but there is not a single breakthrough that made that possible. It's a combination of a lot of little technologies that we already had on Earth that have been used for different programs at NASA, and you just have to put it together.
Right, thank you. Diego Clautau thanks you for sharing with us your experience, and he would like to know, what chance has NASA of finding life on Mars? What are your personal expectations about finding ancient remnants of life?
So I'm an engineer, so I'm not a scientist, so I want to make sure that you understand that. And I can tell you what I know. There are places in Earth that people has been able to find inside clays some basic forms of life, microbiological life that still is inside those clays. So we're going in Mars, the Jezero crater, from measurements from an orbit, from instruments, we know there are similar clays. So I think that getting those samples back, bringing it back, could have a surprise for us. I don't know if Mars had life at the end, but I think it will be really exciting to see it. And if it's not life per se, maybe there are chemical signatures of life like you see on Earth. There are very clear signatures of life on those clays. So I'm very excited for that. The other thing, I'll tell you my personal opinion. You look at our solar system, there are 9 planets or 8 planets, whatever you want to call Pluto. And they're very different, but you look around other stars and other space agencies with their new suite of instruments are finding hundreds of planets around other stars. Could it be that Earth is just the lucky one that has life? I don't. The probability of that to me is very small, and they're so diverse that I think I'm personally think that it's very likely, in my own personal opinion, that it's life out there. It might be. I don't know what kind of life there will be, but I think it's very likely to be there, and it would be really exciting to confirm that at some point in time.
Right, because it's infinite. Dr. Brugarolas, our student Rafaela Orlangi asks if it is possible for human beings to live on Mars and to build a space station there.
So NASA has plans to send human. It is possible, but it's very hard. Just to tell you a few things. Mars has a very thin atmosphere. It's like 1%. It's mostly carbon dioxide. You have bring machines to take that carbon dioxide and get oxygen out. So you could do that. You will also, as you can see, Mars is dry. You need to bring whatever water you need, or basically extract it. And the other thing that is harsh at Mars is that because it's a very thin atmosphere, the atmosphere is what protects Earth from the radiation. It's very thin, so you will have to basically have radiation suits all over. That is to protect yourself from radiation. The other thing that is harsh on Mars is because of the thin atmosphere is the change of temperature between day and night is very extreme. It's even bigger ranges of temperature than here on the deserts in Earth. So you have to make sure that you have to build all that infrastructure for that. And then you all need all that technology to basically land on Mars, whatever space station you have, which could be very heavy. You will need very large vehicles. And also you need a way to get back. So you need rockets that could launch you from Mars back into orbit and then catch a ride from satellite back to Earth. So it is possible. People has plans, but they are very ambitious. There is and actually there's not only plans that NASA is putting together. It's time away. NASA has their own plans. It's developing technology. NASA, as the first step to go to Mars, wants to go back to the moon and develop a lot of that infrastructure to get to the moon. To the moon, because gravity and all that is a lot easier to go than Mars, and then take the next step to Mars. There is also companies like SpaceX that actually want to go to Mars, and they're developing the programs. So we're also excited to see what the private sector will do, and maybe who knows who's going to be first.
We have one other question from a student, a question from Walter Sanchez, asking if, since there is no oxygen in space, is it possible for rockets to catch fire? Or does the lack of oxygen stop that, inhibit that?
So that's correct. If you don't have oxygen, the fire will not burn. But you could, if you could have a fire in space in terms that you can have an electronic failure of a computer or some electronic board, it's hot, and it will basically ignite the materials. It will not propagate like it propagates through the air, but you will get a chemical decomposition with a very high because of the very high heat that is generated by a failure in an electronic component or something like that. So you do have fire, and that could cause damage to nearby components if you were to have a very high energetic dissipation. The other thing that is the challenge is actually a lot of our propulsive systems are highly pressurized. So if you were to have some kind of accident like a micrometeorite hitting and penetrating through the structure, it could create a sudden burst that will also create a very large rate of energy that could also damage things substantially. So space has their own challenges. There are of different kinds.
Joe, eu acho que você só precisa desmutar o microfone. Joe, poderia repetir?
I'm sorry, I'm coming back. No, Sergio Bleckmann, I'm passing over to you. Eu acho que vamos falar sobre a semana que vem ou já agradecemos?
Pode agradecer ao Dr. Paul Brugarolas, depois a
Okay,
gente já
thank
introduz a semana que vem. Eu só queria corrigir, porque eu acho que a última questão foi do Matheus Peloso, nosso estudante, né, Joe?
Thank you. I thank you for the opportunity to talk to you.
Sergio, do you know what our last question is?
A nossa última questão é do Walter Sanches, né?
Ok. Pode falar.
Qual tipo de computador e operação o Perseverance precisa? Acho que você pode endereçar essa última questão.
This is asking about the computer. What kind of computer is required on Perseverance? How does it work in terms of software, hardware? Could you give us some information about the computer on Perseverance on board?
I can tell you, I don't know a lot, but what I can tell you a little bit about it. Because we are in deep space, because of the solar radiation, the computers need to be radiation hardened. So it's a technology that it takes, basically you have to add protection in the computer. And that basically, the computers that we use are, I believe there are power PCs. And these are computers equivalent to what the old Macintosh used to have. Because of the radiation hardening, they cannot go to a very fast clock speed. If I'm correct, I think they run at 133. Well, actually, I forgot the speed of the computer. But anyway, they tend to be quite slow. So we need to put it, when we design the software for these computers, we need to pay a lot of attention. It's all custom software. We need to pay a lot of attention for the computational loading, such that it has enough time to do all the calculations over time. As you can see, when we're flying the vehicle down, we're flying to Mars, flying very fast. So we need to have a computer that's fast enough that could react to it.
For you to communicate with the computer, the messages must take a long time, though, between Earth and Mars.
Yeah, so the communication from Earth to Mars is going to be roughly 8 minutes one way. So you send a command, it takes 8 minutes to get there, and it takes 8 minutes to come back. However, the way we land on Mars is all autonomous. There is an autopilot that basically will fly the vehicle on its own. We're going to send a command that says land, and it's going to go land on its own.
Okay, thank you.
Joe, eu acho que é hora de encerrar. Talvez seja o momento de agradecer demais ao Dr. Brugarolas.
Dr. Brugarolas, we thank you so very much for this fascinating talk. We have all learned so much, and tomorrow it will be so exciting to see this launch, already knowing what is going to happen in the very near future. Thank you so much. And on behalf of the school, honestly, thank you so much for your time.
Thank you for having the opportunity to talk to you. It's fun to talk about what one does in their work, and also hopefully helps motivate others to follow similar paths in science and technology. I have to say, this is the best job that you can have. It's like you go to work, and it's funny that you get paid for doing this because it's really fun. So anyway, if you guys are deciding what to do in your future, take that into account. Pick a job that you're gonna enjoy every day, that is fun and it's exciting, and thank you. I hope that you enjoy this talk today.
Thank you so much.
Thank you.
And Sergio Bleckmann, I think you have a couple of words that you want to say.
Dr. Brugarolas, thank you so much. E queria agradecer muito a nossa comunidade do Colégio Catamarã, que esteve conosco nessa live. Joanna, você quer fazer o anúncio da próxima live em inglês para o Dr. Brugarolas nos acompanhar?
Okay, let me just open it. Colégio Catamarã, we offer lives every week. And this today we had the honor of speaking to Dr. Brugarolas. And next week, our special guest will be Alberto Salvo, a Brazilian environmental economist who obtained his PhD at the London School of Economics and who has worked for many years at Northwestern University in Chicago. He is currently a researcher and assistant professor at the National University of Singapore and will talk to us about the impact of society in the environment. The special live will be on Wednesday, August the 12th at 7 p.m. I hope you join us, Dr. Brugarolas, watching Alberto Salvo. Thank you. Sergio Bleckmann, I pass the word over to you.
Thank you.
Muito obrigado, Dr. Brugarolas, muito obrigado, Joe. Então, lembrando, o nosso convidado especial da live da semana que vem é Alberto Salvo, economista ambiental brasileiro que obteve seu PhD na London School of Economics, trabalhou muitos anos na Universidade Noroeste, em Chicago, e atualmente pesquisador e professor na Universidade Nacional de Singapura. O professor Alberto Salvo falará sobre o impacto da sociedade no meio ambiente. Então, todos atentos à agenda de lives do nosso colégio sempre. E, por favor, não percam na próxima quarta, então, 12 de agosto, às 19 horas, a live com Alberto Salvo. Gostaríamos de agradecer ao Dr. Brugarolas, à professora Joanna, a toda a nossa equipe e a todos os nossos queridos alunos, pais e professores do Colégio Catamarã. Muito obrigado a todos. Até mais.